What's up, guys, and welcome to this video. We're going over question 4 of the 2017 supplementary exam, which covers Newton's laws. Okay, so this is a graph question. Maybe I'll skip this and just do from 4.2. I don't like to do these graph questions because I can't draw one accurately without a graph paper sheet. Okay, let me just explain how to do this question then. Okay, so question 4.1. An experiment was conducted to investigate the relationship between force, so between the force exerted on an object and the object's acceleration. Okay, so an electric fan is mounted on a zero friction cart to accelerate the cart along a smooth track. The speed of the fan and hence the force exerted is adjusted and the acceleration of the cart determined. Okay, so the force exerted on the cart is adjusted and the acceleration of the cart determined. Okay, cool stuff. So the point of this experiment was to determine the relationship between force exerted on an object and the acceleration. Okay, do we know an existing relationship? Well, we actually do. If we know that the force, the net force, is equal to the mass times the acceleration. So we have a relationship between the force and an acceleration. Okay. So question 4.1.1, name and state the Newton's law that is under investigation. Okay, so we already kind of did that. So we know that it is Newton's second law, and the definition for Newton's second law is when a net force acts on an object, the object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass. And we get that equation from the definition. Okay, so we get 3 marks for figuring out what Newton's law it was and giving the relationship. Okay, so state the dependent variable in the investigation. Okay, so the dependent variable is the variable that gets changed, or okay, so the variable that is under investigation. Okay, so if we read the first sentence, it says if we want to investigate the relationship between the force and the object's acceleration. Okay, so those are our 2 variables, and we know that the speed of the fan and hence the force exerted, so the force we are controlling, so that is the independent. Okay, so the acceleration of the cart is to be determined. So that's the characteristics that's under investigation, and that's the one that the force will affect. So the dependent variable would be the acceleration. Okay, so the acceleration is the variable that changes as a result of the force. Okay, so next we have to draw a graph. Okay, so plot a graph of acceleration. Okay, so it's going to look something like this. So it's going to be acceleration. Okay, so they want that on the y. Okay, acceleration is in meters per second squared against force. Okay, so against force, and that is in millinewtons. Okay, so the milli represents times 10 to the minus 3. Okay, so they want us to sketch that. Okay, so obviously I'm not going to sketch it accurately at all, but essentially it should go, we know that when there's zero force, there's zero acceleration, and when there's maximum force, there's going to be maximum acceleration. So it probably is going to look like that. Okay, and we also know that the slope is going to be a straight line graph because of this relationship. So we're plotting forces and accelerations. So the variable that's left is the mass, which will be the gradient, or it could be the inverse of gradient. In this case, I'm sure we'll have to figure it out, but let's just do this. So our gradient is equal to our acceleration over the force. Okay, acceleration over the force. So if you rearrange this equation right here, acceleration over force is equals to 1 over m. So our gradient is equal to the inverse of mass. Okay. Okay, cool stuff. Calculate the gradient of the graph, include the appropriate units. Okay, so the gradient of the graph. Okay, also don't forget your graphs need a title. There's going to be marks allocated for that kind of stuff. Okay, so to calculate the gradient, we would pick 2 points somewhere, and then we do change in y over change in x. Okay, to get the units for the gradient would be, okay, so we don't actually know how heavy this cart is. It's probably, okay, so because they haven't told us the units of the cart, we can either pick that the cart is very small, in which case it would be mass of the cart is in grams, or if it's a heavier cart, we can pick mass of the cart is in kilograms. Either would be correct because we haven't been told anything. Okay. Okay, so we already calculated that the gradient is 1 over kilograms. So the units would be equal to kilograms to the minus 1 or grams to the minus 1. Like I said, it doesn't really matter as long as you keep it consistent because we haven't been given the mass. Okay, then use your answer from the previous question to determine the mass of the cart. Okay, so 1 over mass is equal to our gradient. Okay, so to get the mass would be equal to 1 over the value that we calculated before, which is our gradient. Okay, and that would have units of kilograms or grams. Let's say, or grams. Okay. Okay, so that's that. Then it says the experiment is conducted again, but on a track with friction. The cart experiences a frictional force of that many millinewtons. Okay, so now there is a important constant frictional force. Okay, so with a constant frictional force, what we're going to have is that, first of all, our force is going to shift because it's not, we need to exert a force before it moves. So this is going to move, so x-intercept is going to move to 50. Okay, and the reason that happens is because there's a constant frictional force. If it's less than 50, if the applied force is less than 50, we have no movement. Okay, so after 50, the mass, or the inverse of mass, the mass of the cart does not change here. So that means the gradient cannot change. So what we're going to have is, we're just going to have a line which is parallel. So we're going to have a line that is parallel to the line before. Okay, and the accelerations would be less because now there is friction being introduced, but the gradient is still equal to 1 over mass. So the gradient remains the same. So these two are parallel, but you don't have to show the parallel lines. Okay, so that would be your answer. And we get 2 marks for that. Okay, now we're getting into a real question that does not involve the graph, so I'm going to be doing this. Okay, so a box of mass 150 kilograms is prevented from sliding down the slope by a force of 100 newtons acting at a 40-degree angle to a rough inclined plane. So I'm just going to put in there that there's also friction. Okay, because it's rough, the plane is inclined at 35 degrees to the horizontal, and the coefficient of static friction between the box and the surface is Okay, so mu is equal to 0.7. Okay, cool stuff. So question 4.2.1. Okay, so question 4.2.1, draw a labeled free body diagram showing all the forces acting on the box. Okay, cool stuff. So I'm going to start off by drawing our slope, which is something like that, at an angle of 35 degrees. Okay, and here goes my free body diagram. So we're definitely going to have a weight force. Okay, also there is a slope, so we're going to have a normal force. Okay, we know that there is a force upwards being applied. That is the force yeah, we can just leave that as force applied. Okay, and that's also at 40 degrees. Okay, I'm just going to keep that in my head by circling that. I'm not going to put it in the diagram. And then we're also given that there's friction, and friction acts parallel to this surface. So we have force friction. Okay, and that's our labeled free body diagram, which we get 4 marks for. Cool stuff. Okay, so calculate the component of weight parallel to the inclined surface. Okay, so we know that there is a component here. We can call this F perpendicular, and we know that there is a component here that is F parallel, and we also know that this angle in between here is the same as the angle of the slope, which is 35 degrees. Yeah, okay, cool stuff. Now we can go on. So 4.2.2, calculate the component of weight parallel. Okay, so I'm going to say the force parallel is equal to weight. So that's weight, and we're looking for parallel, which is sine. So opposite, sine 35 degrees. So that's equal to, our weight is equal to our mass times our gravity, sine 35 degrees, which is equal to a mass of 150 kilograms. Gravity is a constant, which is 9.8 sine 35. So we have F parallel is equal to, if we plug that in, we get 843.16 newtons. Okay. And we should actually give a direction because that's a force, and we can say down the slope. So the direction is, it's acting down the slope. It's acting in that direction. Okay. Then, okay, so that we get 3 marks for. Cool stuff. So question 4.2.3 says, calculate the magnitude of the frictional force acting on the box. So what we want is force friction. Okay, so how are we going to do this? Okay, so what we're going to do is I'm going to say, we know that it is held stationary by that force because it's prevented from sliding down the slope. Okay, so what I'm going to say is that the sum of the forces in the downwards direction, okay, is equal to 0 because it's not moving, right? If it was moving, it would be equal to mass times acceleration, but it's not, so it has to be equal to 0. So what we can say, I'm actually going to take that output direction as being the positive direction. So what we have is force friction. So force, okay, let's say force friction. If we look at our free body diagram, okay, so we have the force friction, which is acting upwards at this angle of 40 degrees because we just want the component like this. So that's the angle. So force friction, okay, so force friction plus force applied, but we just want that component acting on the surface parallel to it. So that would be our cos. So this force applied can be broken Okay, force applied can be broken down into a force like that and a force upwards. So I just want this component right here. So that would be with an angle of 40 degrees. That would be our cos 40, okay, minus, we have the only force acting in that downwards direction is our force parallel, is equal to 0. So we can say that the force friction is equal to our force parallel minus our applied force cos 40. So what we have, we calculated the force parallel, which was 843.16, minus the force applied was 100 newtons cos of 40 degrees, and our force friction is equal to 766.55 newtons, and we just want the magnitude, so we don't care about the direction. And we get ourselves 4 marks. Okay, cool stuff. Then it says, the size of F is slowly reduced from 100 until the box is about to slide. Calculate the minimum value of the force F for the box to remain at rest. Okay, so we want the minimum value of the force F for the box to remain at rest. Okay, how are we going to do this? Okay, so what we're going to start off by looking at is, let's look at the downwards components. Okay, so we know that the sum of the forces, I'm going to take it down as being positive, must be equal to 0. Okay, so we know that because we want it just before it starts moving, and it will be moving down that slope. And we also know that we want the sum of the forces, but this time we want it, we're going to be looking at it in the upwards direction, perpendicular to the slope. So in this direction here, it might not be drawn too great. In this direction must also equal 0. Okay, so this one is because no sliding, and this one is because it must be in contact with slope. Okay, so I think if we do those two, if we figure out those two, eventually we'll get to the minimum value of F. Okay, so now I can use my free body diagram and get these equations. Okay, so looking at, let's clean this up actually. Wait. Okay, cool. So first we worried about down the slope. Okay, so the forces acting down the slope is this F parallel. So let's take F parallel, okay, minus, what do we have? Force friction minus this this force, the applied forces component, that component right there. So minus F, which is the applied force, and we know this angle is 40, so F cos 40 is equal to 0. Okay, and that we can say is going to be equation, okay, now let's actually rearrange that, and we can say F parallel we know is M. Okay, so we can say that F parallel is equal to force friction plus F cos 40. Okay, but we also know that F parallel is equal to mg. Mg, and the angle is 35, so mg sine 35, okay, is equal to the force friction plus F cos 40. Okay, I'm going to let that be equation 3. Okay, then we're going to look at perpendicular to the slope, with the upwards being positive, so we have the normal force, so let's say Fn, okay, plus we have this component of the applied force, which would be F, this time it would be sine 40, Okay, and the only force acting down the slope would be this force F perpendicular minus F perpendicular, which would be mg, this time cos 35, is equal to 0. So I can rewrite this as F normal plus F sine 40 is equal to mg sine, oopsie, not sine, but cos of 35. And I'm going to label this equation 4. Okay, let's get rid of this. Actually, I don't need it now. Okay, so let's look at what we have and what we need. So we know what mg sine 35 is. We don't know force friction. We don't know force applied. And we know what cos 40 is. We don't know what force normal. We don't know that. We know sine 40. And we know mg cos 40. Okay, so we have two unknowns and two equations. Cool stuff. That's always a good place to be. So let us rearrange this equation 3. So equation 3 can be written as mg sine 35 is equal to mu times the Mokada! Yeah, fucking up. Okay, let's try rearrange equation 3. So we have mg sine 35 is equal to our force friction, which is mu times the force normal. Okay, plus F cos of 40. Cool stuff. Now we can get force normal. So if we want the normal force, we can say that the normal force is equal to, let me actually do it here. We can say the normal force is equal to mg cos 35 minus F sine 40. Cool. Now we have mg sine 35 is equal to mu times mg cos 35 minus F sine 40 plus F cos 40. Okay, so let's see. We have mg sine 35. We know what mu is. We know what mg cos 35. We don't know what that is. We know what sine of 40 is, and we know what cos of 40 is. So we know what F is. Okay, cool. So we have one unknown. So we can just solve this. Let me get it a step further. So we have mg sine 35 equals mu mg cos 35 minus mu F sine 40 plus F cos 40. So we have, pulling this that way, we can pull out mg. So we have mg sine 35 minus mu cos of 35 is equal to, pulling out F, we have mu sine, pulling that out, we have F here, but I'm going to put the positive, so F cos of 40 minus mu sine of 40. Cool. Now we have one unknown. These are all known values, so we can just solve for F, and we get that F is equal to 0.79 newtons. Okay, so quite a lot of work for that question, considering it's only worth 4 marks. But basically, once you get equation 3 and 4, everything else is just maths and manipulating equations. Okay, guys, yeah, so thanks for watching, and I hope you guys found that video useful.